Students, today is a momentous day for the 5 of you that are going to watch this. We're going to talk about cross products. We need a little bit of math so that you can do the physics appropriately. Now, this is the thing, is that I'm going to say a few things in this video that may not make sense until you've taken linear algebra. It's okay. It's not anything, it's not anything weird. It's just that I'm going to define a bunch of math, and then you're going to see it later. If you're in vector calc, you've probably seen some of this. This is not new stuff. It's just different. It's going to be presented differently. Okay. So we have vectors. Let's draw some vectors. Let's draw in A, and so we put that in green. We're going to draw in B here in red. All right, we're going to autofocus. All right, so we've already talked about one way of multiplying these together. The idea is that we multiply these two vectors together and we end up getting a number. That seems like an odd thing to get, right? But we've already defined that is length of A, length of B, cosine of this angle theta that's in here is going to be A dot B. That's going to be our definition for the dot product, right? Well, what if we did something else? What if we did A, B, sine theta? What does that equal? Well, what happened here is when we took A dot B, let's pull up a blue marker here. There were two components to B. There's this one I'm drawing in, which is B sine theta, and then there was this one along A, which was B cosine theta. So this one is saying, this thing that I'm looking at first, I'm saying, I just want the part of B that's along A. This one is saying, I want the part of B that's perpendicular to A. So I still have two vectors, and they're kind of spread out a bit. And I'm going to repeat draw these. All right, so I'm going to draw B in. And I'm going to draw A in. And I'm going to copy A up here. And I'm going to copy B down here. Now that kind of makes a little bit more sense, in the sense of what we're kind of doing is taking and trying to find, essentially what we're trying to do is find the area of this thing I've just drawn, a parallelogram I've just laid out with these two vectors. And that's what AB sine theta does, is it gives you a number that calculates essentially this area. So this thing here that I've drawn, this whole thing has, in math, it has a name. It's going to be A wedge B. And so this thing is not a vector, right? Remember, A dot B is not a vector. It's a number. This thing is not quite what we think. This thing is sketching out this area that's trapped between these two vectors here, these four vectors, the two representations of two vectors. This thing is what's called a wedge product. And what this represents is a bivector. Now, that doesn't sound like anything useful to us at the moment, right? That's still kind of, why would we ever bother to know that? But I mean, one of the things might be calculating the area of something where the sides of it are represented by two vectors. Right? That's not an unbelievable thing to do. You may also see this in the literature as a pseudo vector. Assuming you read the literature on cross product, why would you do that? But the point of this is, this thing in physics, AB sine theta, is a thing we treat as a vector, and it is A cross B. And these things are related. The idea is this thing, which represents the area, has a vector associated with it. What we've done is we've drawn a sheet of paper. So I have a sheet of paper here. What I'd like to do is discuss a direction that's associated with this piece of paper. And if I hold it up like this, the other side is your grading stuff for your science fair. If I hold it up like this, we can ask, well, which way is the front of the paper pointing? And it turns out it's in the direction of my ink pen. It's that way. There is a definable direction. Now, you can define the other direction the same way. There's an ambiguity here. And so the way we're going to define it is going to make sense like this, or out of this piece of paper, it's going to be straight up towards the camera. So for this A and B here, what we're going to do is define, I'm going to put it in purple so you can see it, a single vector that stretches up and is perpendicular to both A and B. And this is going to be A cross B. And it's going to its length is going to be the area of this thing, and its direction has to be perpendicular to A and to B at the same time. And the reason we're picking the upward one is going to be based on the things that we talked about in the lecture slides, which I'm going to go over in a minute. Basically, you have two hands, right? You have the right hand rule that we discussed in the slides, and you have a left hand rule. You have to pick one, and we're picking the right one. So we're going to sketch this out actually, we can do it with this. So I'm going to rotate this. Your first finger is going to be your first vector, is A. Your second finger is going to be your second vector, is B. Note that I've laid it out. A goes that way and B goes that way. And your thumb, my thumb is curved, but your thumb represents A cross B, which is up in this case. So there's a few other things that we could do to define this A cross B. One of them is to write this out in components. A cross B is, and now this is where it gets awkward. So I'm going to teach you what's called the determinant. Let's say I have a matrix, and it's going to have here, first our unit vectors, and then it's going to have our components of A, AX, AY, AZ, and then it's going to have BX, BY, and BZ. So what we're going to do is, for each one of these unit vectors, we're going to associate it with this smaller bit of this matrix. And we're going to do that over and over again. But what we're going to do is for the small bit of the matrix, the determinant is defined as the diagonals subtracted from each other. So we'll do AY BZ minus AZ BY. And this is a thing that is associated with the I hat vector. So we'll write in A cross B equals, and then we have this term here. Then for the J vector, we're going to ignore that line, and we always ignore this. And so we're just going to have this bit and this bit. And we can rearrange these as long as we move one of these a couple over. So this is going to end up being, we're going to start here, and I'm going to copy this over AX BX. Right? So it's going to be plus J hat AZ BX minus AX BZ. And finally, in green, this stuff comes from this corner. And so we'll have plus K hat AX BY minus AY BX. Now, that probably makes next to no sense to you. That is okay. We're almost never going to do this personally. But if you're in vector calc, you've seen this before. If you're in linear algebra next semester, you will see the determinant. And the idea is that for something that looks like, not B here, D, or something that looks like A, B, C, D like this, the determinant is A, D minus BC. And then for the three-dimensional thing, the determinant of this is I hat, and then the determinant of this stuff plus J hat times the determinant. And the idea is that you make smaller versions until you get down to this and you can solve it. So it makes this complex, ugly thing. And there's a reason why we're going to stick with the very basic stuff. A cross B is AB sine theta. Sometimes we use phi instead of theta. I think the notes actually use phi, but that's okay. So there is reason I want to bring this up, and it comes from talking about what happens with A and B. When is this thing zero, basically? If A and B are parallel in some way, you're going to get that some of these terms cancel each other out so that you get zero here. In particular, if A and B are only in the x direction, then your y and z parts are zero, and so this determinant is zero. Alternatively, from this definition is much easier. If they're parallel, sine is zero, and either phi is 0 or 180, and so sine of theta is 0. So you get some things that you learn is A cross B is 0 if sine theta is 0. Or A cross itself is always 0. Because by definition, a vector is parallel to itself. Now, there's also the bit that we talk about a little bit about A cross B is minus B cross A. So there's a reason for that, and it has to do with the right-hand rule. All right, so we have a right hand. What we're going to do is draw A, And then somewhere else we're going to draw B. And then C is going to be perpendicular to both. And it's going to be upwards the way I've drawn it based on my right-hand rule. All right, so C is out of the page. So let's draw what B cross minus A would look like. Well, we're going to draw in minus B, and then we draw in A. And then from our right-hand rule, we point in the direction of B, and the middle finger goes in the direction of A, and our thumb is out of the page again. So it's also straight up. And the sine theta bit doesn't care about the signs on here. They're just caring about the lengths. So what happens if we draw B cross A? All right, so this is A cross B. This is B minus B cross A. Well, here's B. And then A is going to go like this. Right? So this is one where we have to kind of contort our hand. So when you're doing what we're talking about here, we're going to rotate the paper often. First finger is B. Your second finger is A, and to point it that way, I have to rotate my hand like that. And that puts my thumb pointing down into the screen. And so C here goes downwards. So there's a couple other things. When we want to draw things in 3 dimensions, right? This is a perspective drawing. These are not in the, C is always sticking out of the page here when I draw this. So well, we actually want to indicate into and out of the page. So these things are arrows. Right? Imagine my pen is an arrow. If I wanted to put the arrow into the page, I would put it this way, and you're looking at the back of the arrow. In this case, the back of the pen. This notation is being derived. Effectively, it's being derived, by people historically who were very into archery. They were, the British have a long history of shooting arrows at things. And so they intended these arrows represent kind of real arrows. If you look at the back of an arrow, there are feathers. So this symbol represents the feathers on the back of an arrow. Now, out of the page, well, this is our arrow. Out of the page is upwards, and you see the point of the arrow. So that is a circle with a dot. And sometimes we neglect and we just put dots or just put X's for into or out of the page. But this is representing an arrow coming at you here and going away from you here. So that's what we mean by into and out of the page. So I'm going to draw a little bit more. I'm going to redraw this picture again because I wanted to talk a little bit about this right-hand rule. So we have A here and we have B here. And so we want to ask, well, which way is the, which way is our right-hand rules going to work? And so we showed you this thing, right? So the idea is you point in the direction of the first vector, and your finger is in the direction of the second vector, and your thumb represents the third vector. You can also express that as, imagine there's this area here. And what you're going to do is use your hand, and you're going to start grabbing it along A, and curl in the direction of B. So when I grab it, I'm going to grab like this and curl. And my thumb represents the direction of that area. So in this case, it would be out of the page. So there's another thing, right? If you remember in the past video, I talked about this operator, which was I hat derivative with respect to x plus j hat derivative with respect to y plus z hat derivative with respect to z. So you can come up with a thing that is the cross product of this with a vector is the curl of A. Right. Now, we also talked about the dot product. The dot product of A here is what's called the divergence. Right. But what this is it's telling if I have some set of vectors, how does it wrap around some other point? How does it curl? How would I turn my hand around, make it make sense? And if all my vectors are all in a straight line, then there is no curl. So this exists. You don't have to worry about it. So that's where I'm going to stop the video. We're doing these cross products. And in the notes, I just give you the definitions for them in terms of components and in terms of the right-hand rule and this geometric definition. All right, so we're actually going to apply this in a little bit. We're going to use it to talk about motions of different things. Now, I mentioned in the notes right-hand rule number 2. In the next video, I'm going to define the right-hand rules so they make sense to you.